All right, so this video covers rigid body kinematics 1 and 2, starting with kind of the description of the different types of motion, and I kind of want to go into a little bit how to identify what they are. So the different kinds of motion are rapha, which is just rotation of any kind, translation, which is just like any kind of sliding, either in a straight line or in a circular path, and then GPM is just this awkward combination of both of those, right? So the real trick is to identify if it's one or both of these, right? And if it's both of these, it's going to be that. So in terms of identifying them, it's going to be rapha if there's some kind of fixed point and this point's moving, right? So if this is fixed and this is moving, the only thing this body can do is rotate, right? For translation, it's going to be anytime the body can slide. So most commonly, that's if there's like a block or a point or something like that inside of like a track of some sort. And say like there's a bar connecting that, and then this side of the bar is along a piece that can just slide this way. This sliding is the translation part. So because that can only translate, you're only going to call that translation. And then, for example, if there was a bar and this side was translating and this side was rotating, or both of those sides were free to move in any direction they wanted to, that would be general plane motion. So that's probably the best way of thinking about it. If one side is fixed and the other side spins, that's rapha. If the entire body is inside of a track of some sort or is limited to only moving in one direction, that's translation. And general plane motion is if both sides are free and able to move however they so please. So that's kind of the big thing, is being able to identify the types of motion, because that's how you go into the rest of the problem. So for a rapha stick, right, you have the linear components of the velocity and acceleration at the end of that rapha stick, but along the entire length of it, you have the angular components, right? Because they rotate, you can measure it in terms of the angular quantities. And those quantities are related to each other, right? So the velocity and the angular velocity are related by v equals omega r. And the accelerations in both directions and the angular acceleration are related by a few equations. So at is alpha r, and that kind of goes along this direction. And the normal acceleration is actually a function of the angular velocity, right? So it's not necessarily related to the equation for acceleration, but it is a quantity related to the angular velocity omega. And then the position and the arc length, that's just theta r. All of these, I believe, are on your data card. The only thing to remember is that when you're drawing these rapha sticks, you want to draw all of the equivalent quantities in the same direction. So like if velocity is pointing up and to the left, omega should be pointing so that it rotates in that same direction, right? Because if this point is moving that way, it would make no sense for this bar to be falling clockwise. So just kind of double check that when you draw your rapha sticks, that all of your quantities that are like related to each other are in the same direction. So going into rigid body kinematics, basically the entire point of it is to relate the body properties to a specific point along that body. So what you're going to end up doing is, if you're given a body property, which is any of the angular quantities, you're going to want to translate that to a point property. Most commonly, you're going to be given a point property, and then you're going to have to translate that to a body property, and then go back the other way to a point property to describe a different point. And that change is usually going to be the radius term. So, yes. One thing that we brought up last time, especially with the relative velocity stuff, is these kinematic diagrams. I don't know if Dr. O'Neill stressed the importance of them, but I know Dr. Liao didn't explicitly say that they're mandatory. But in terms of like the grading rubric, it's absolutely mandatory. Like just like a free body diagram, it has points associated with it. And because of that, you have to do it and you have to do it right. So that's something that I would absolutely, absolutely practice, because if you don't do it right, you lose points off the bat over something that you're really doing in your head anyway. So make sure on your kinematic diagrams, you're including all like motion. So all of the velocities, both linear and angular, all of the accelerations, linear and angular, and any dimensions and point labels. So from those kinematic diagrams, you're going to end up writing your X and Y equations, and then you find your unknowns. The important thing to realize is this pattern that you're going to be switching between point to body to point to body to point to body as many times as you can until you get to the point, or until you get to the quantity that you need, right? So it's just get used to point to body and then back and forth. Rigid body kinematics 2 goes back into relative velocity, but it's relative velocity in terms of one point, or on multiple parts of a composite body, right? So step 1 is still classify motion. And again, like just like the kinematic diagrams are required, this piece right here is actually required. So like on the drawing that is attached to the worksheet, like the printed drawing, literally write on the body what it is. So if like one piece is RAFA, literally write RAFA on the drawing, because this is points. So again, RAFA is, can it rotate? So if it's rotating, it's RAFA. If it's translating, can it slide? Translating is the actual like motion in 2 dimensions. And then general plane motion is RAFA and translation combined. So the idea behind rigid body kinematics to find linear velocity or relative velocities is that you kind of want to take one common point and write the relative velocity equations for the body to the left of that point and the body to the right of that point. And because that point attaches both bodies, you have to know, or it has to be that these 2 equations equal each other, right? So V common equals V other 1 plus V common over V other 1, but also V common equals V other 2 plus V common over other 2. These have to equal each other, and it's that principle that allows you to solve these this way. So V other 1 and V other 2 are basically the endpoints of like, or the points on the opposite side of the member from the common point, right? So that's just going to be the velocity of that point. Sometimes it'll be fixed. Sometimes it'll be translation. Other times it'll be, you'll be given some kind of angular velocity and you'll have to translate that. Usually these are known, right? The V common other and V common other here, like with respect to the other point, those are going to be drawn as RAFA sticks, where this point on the bottom is the one that's fixed. So basically, regardless of whatever the member is, like even if it's general plane motion, right, you're going to approximate it as RAFA. Okay, so just for this second term and this fourth term, just for these 2, you're going to approximate it as RAFA, where this bottom point is fixed, where the other point is fixed, and the common point is the one whose velocity you're assessing. So once you find all these kinematic diagrams, you're going to set up your equations for X and Y. The important thing you're going to watch out for is the sines and cosines, because now everything's going to be connected and usually it's at a really awkward angle. So make sure you're watching sines and cosines, or your slope triangles, whatever they give you. But you're going to end up setting up a numerical representation of your kinematic diagrams in the X direction and the Y direction. And because you only have these 2 equations, you're going to only have the 2 unknowns between the equations, right? So you should only have 2 distinct unknowns between the equations. And the only thing that really kind of trips people up in these problems in terms of like losing points is if you stop too early or keep going too long, right? So what I mean by that is, for example, if the question asks for the angular velocity, right? But you, in your kinematic diagram equations and the kinematic diagrams and the scalar equations you get from them, you ultimately solve for linear velocity. Some people will forget that they need to switch from linear to angular because that's what the question is asking for. So make sure that you are able to use the answers you get from your scalar equations to find the ones that it's asking you for in the question. And then I guess in terms of your answer, you should have a magnitude, a unit, and a direction, kind of like normal. This is just reiterating the steps. I kind of went over them already, so I'm going to skip this, but definitely read it. Yeah, I went over all this already. The only other new thing for this, I guess, lesson is the introduction of no slip wheels. So no slip wheels are wheels that like cause motion. So if this thing is rolling this way, this point is rotating, right? So it's not just stationary. It's not essentially doing like a burnout. It's actually like with a roll comes like translation, right? So because every point on this circle is both rotating and translating, every single time it's going to be general plane motion. And that's something that you should absolutely try to commit to memory because this is a common component in the problems that they give on quizzes and exams. So you're always going to call the point of contact between the wheel and the ground the fixed part of a rafa stick, right? And then depending on what point on the circle it's asking you for, the point on the wheel it's asking you for, you're going to pretty much just draw a line. Your rafa stick is going to go from the point of contact to the point. So anytime this no slip wheel is attached to another member, so say there's a stick coming out of here and it's pinned at the origin, your rafa stick is going to be from the point of contact to the origin, right? But if you're going the other way around, or if you're specifically looking for a point on this edge for whatever reason, you draw the rafa stick from the point of contact to the point you care about, right? So the omega should generally stay the same. I mean, I drew two different ones here just to show that it doesn't matter and that's clockwise or counterclockwise, but regardless of what point on this wheel I'm looking at, the omega is going to stay the same because it's all on the same wheel. The omega is a body property. The rafa stick is going to connect the point of contact to any point, so that initial point is going to stay the same. The only thing that changes is what point I'm looking at, right? So if I was looking at the origin, this is my rafa stick, so there's an associated length of the rafa stick, right? But if I was looking at the point over here somewhere, now this is my rafa stick. So that length changes. So the only thing that changes is this r in this equation, right? So that's the important thing to know. And then again, I'm going to keep annoying you guys with it at the end of these videos. Shameless plug for the best office hours on campus. These are the hours. The Zoom link is on Canvas. I'm there 5 hours a week, so please come visit me because I get bored. We can do any of this stuff. And yeah, if you have any questions, feel free to text me. If not, I will see you guys in class.